Welcome back to my R-44 helicopter project. I've made previous comments to this channel about the inflow angles to helicopter blades and how these angles affect and are affected by rotor blade motion and control. A few of you pointed out that I never fully explained some of these concepts. Today I'll do a more in-depth look at blade twist, induced flow, blade section angle of attack, and hover aerodynamics. This will include the aerodynamic force that allows autorotations and why, during autorotations, there are driven and driving regions on helicopter blades. Thank you for subscribing to the channel. I make content based on subscriber comments, so please let me know if you have any questions and what you'd like to see in the future. The size and angle of the aerodynamic vectors in my past videos wasn't based on analysis. Instead, I made them look about right based on my knowledge of helicopter aerodynamics and illustrations from textbooks. In this simulation, I now have vectors for rotation speed, inflow speed, which is also called downwash, blade pitch angle, the total velocity vector, and the net aerodynamic force vector. The difference from my previous projects is that these vectors are now driven by equations that came from a hovering analysis of an R-44 helicopter. I used both momentum theory and a blade element analysis to develop the equations that drive the simulation. And my primary reference for this project was Aerodynamics of the Helicopter, written by Gessow and Myers. In a few minutes, I'll go into details on the theory and math that allowed me to create this simulation. First, let's talk about why we're interested. This analysis gives a good insight into how helicopters work, and the most insight comes from observing the net aerodynamic force vector. As I change input variables in the simulation, the magnitude and direction of this vector changes. For a hover analysis, the most significant variables are the radial position along the blade, the collective lever position, and the vertical descent rate. I hope to take this to a forward flight analysis next to include flapping and forward flight dissymmetry of lift effects. For today, it's hover only. We call this a net aerodynamic force because it has both horizontal and vertical components. The vertical component is lift and the horizontal component is drag. By switching to this side-on view, you can see the vector tilt as I raise and lower the collective lever. Tilt is what creates the horizontal component of the force. I'm demonstrating how small this component is in comparison to the vertical component, but that small change has a big impact on how helicopters fly. It generates most of the drag that's normally overcome with engine power, and it's the aerodynamic force when it tilts forward that allows autorotation. In fact, in non-rotating wing aircraft, this same force vector, when it tilts forward, is what allows airplanes to glide. When the net aerodynamic force vector tilts aft, when the pilot raises the collective, induced drag becomes higher. And this has a tendency to slow the rotor, to decrease the RPM. We don't want the rotor to slow down, so we have to do something about it. And that something is to add more torque to the rotor by opening the throttle in order to increase engine power. This could be done manually by the pilot, typically with a twist grip throttle on the collective lever. But in most modern helicopters, this is now done with a system. These systems have different names, things like fuel control units and digital engine controls on turbine-powered helicopters, and correlators and governors on piston-powered helicopters. Different names and different mechanization, but they all do the same thing. They add more engine power when the pilot raises the collective, and they reduce engine power when the pilot lowers the collective. I'll segue here briefly to mention tilt rotors. The type of system I just talked about is called a throttle-governed system, meaning the pilot sets the collective pitch of the rotor blades, then the system adjusts the throttle in order to maintain rotor speed. But all of the tilt rotors I'm familiar with use what's called a beta-governed system, meaning the pilot sets power and the system then adjusts the pitch angle of the blades. Beta is what engineers call blade pitch angle. It could correctly be called a pitch-governed system, and that term would be less confusing, but beta-governed is the more common term. Despite this fundamental difference, the way pilots interact with the flight controls isn't that much different for most hover maneuvers between helicopters and tilt rotors. Aside from the changes to drag, the other interesting thing about the net aerodynamic force is that it can also tilt forward. At low collective pitch settings, the vector tilts forward to vertical. This means the horizontal component is no longer creating drag. Instead, it's now creating a driving force that motivates blade rotation. This driving force allows helicopters to auto-rotate, meaning rotation of the blades is no longer driven by the engine. Instead, rotation is automatically driven by the forward tilt of this net aerodynamic force. The pilot has to lower the collective lever to do this, and this decreases the vertical component of the aerodynamic force, meaning the aircraft will descend, but it allows the rotors to continue turning and producing lift even without engine power. This is the same aerodynamic mechanism that keeps tilt rotor blades turning in power-off airplane mode flight, and it's the same force that sustains blade rotation in autogyros. I mentioned before how the force vector isn't constant along the radial span of the blade. It changes because of differences in blade twist, inflow velocity, and angle of attack along the span of the blade. These changes create different regions along the blade span. Regions with the force vector tilted forward are responsible for autorotation, and we call these driving regions. Driving because the aerodynamic force is driving the rotation of the blades. The regions that create drag with the force vector tilted aft are called driven regions. The things that cause the force vector to tilt forward are lowering the collective lever, an increase in vertical descent, and location along the blade span, with the outboard sections having more forward tilt than the inboard sections. As I slide the vector in and out, it becomes apparent the driving region is outboard and the driven region is inboard. And I should mention again, this is a hovering analysis, and these regions change somewhat in forward flight. Showing this total aerodynamic force vector was the intent of this video, but now we can get to the fun stuff and talk about the aerodynamic theory it took to simulate this on the screen. I'll start by comparing the helicopter rotor to an airplane wing. In a wing, the angle of attack is the difference between the flight path vector and the chord line of the wing. And a quick analysis of an airplane wing is relatively simple because inflow of air is constant across the span. If you know the airspeed and the angle of attack, this equation works out to a good approximation of the total lift produced by the wing. But we can't use this for helicopter blades. Airplane wings don't rotate or flap like helicopter blades, and while airplane engineers have to account for downwash, at least for subsonic flow, it's relatively small and constant along the span. This isn't true for helicopters. Helicopter engineers, on the other hand, have to account for these things, and these things mean that unlike an airplane wing, each part of the rotor blade sees a different tangential velocity, pitch angle, downwash velocity, and angle of attack. This leads to the fundamental idea of a blade element analysis. Instead of treating the blade as a single wing moving through the air, we divide it into multiple spanwise sections and do an aerodynamic analysis on each separate section. In my blade element analysis, I treated each blade as 10 separate airfoil sections. I did this in a spreadsheet, and then I totaled the contributions of these individual blade sections to find the total lift and drag produced by the blade. The spreadsheet was a way to validate my math and create some charts. In the simulation, the math is not discrete. It's continuously variable along the blade. And let's talk about this math, starting with tangential velocity. This is the air velocity in the plane of rotation that a helicopter generates by rotating its wings. Lift produced on the blade section is proportional to the square of this velocity's magnitude, and we calculate this velocity in a hover by multiplying rotation speed by the radial position of the blade element. This is a linear distribution along the span of the blade, and here's what that looks like for a single R-44 helicopter blade. For an R-44 operating at 408 revolutions per minute, the tangential velocity varies from 0 at the hub to 200 meters per second at the tip. I used SI units in my math. 200 meters per second works out to a standard day tip Mach number of 0.6. And this video describes a hover analysis, but as a reasonableness check, I'll add the R-44's maximum forward flight speed of 130 knots to the advancing rotor. Now the advancing tip speed becomes 271 meters per second, or about Mach 0.8. Helicopter forward flight speed limits are designed to avoid advancing blade compressibility. So a tip Mach number of 0.8 is a good check that I didn't make an obvious math error. Here I'm sliding the vector along the span of the blade so you can see the change to the tangential velocity based on radial position. And by the way, my math assumes the rotors are always rotating at 100% RPM, so you see this effect in my 3D model here whether or not the blades are rotating. Now I've changed the forward flight speed to 130 knots. This is so you can visualize how tangential velocity changes due to the blade advancing into and retreating from the relative wind while in forward flight. And interestingly, when I slide this to the inboard blade section, you can see the part of the retreating blade with this region of reversed flow. I hid the net aerodynamic force vector and the total velocity vector in this forward flight simulation because the only forward flight consideration in the math model is the velocity component. If I were to show these other vectors, they would erroneously show a reduction in lift on the retreating blade. To make this simulation more realistic and applicable to forward flight, I would need to add the forward flight flapping coefficients to the math model. Next, we need to find the pitch angle at each blade section. What we really want is the angle of attack, but knowing the pitch angle is a step towards that goal. Almost all helicopter blades are twisted, with a root pitch angle greater than the tip. Typical values of twist range from 6 to 18 degrees for helicopters and up to 50 degrees for tilt rotors. The reason for twist in rotor blades is an attempt to account for the change in the tangential velocity that we just talked about. Remember, lift is proportional to the square of this tangential velocity multiplied by the angle of attack. Because the blade root has a lower tangential velocity than the tip, having a higher pitch angle and thus a higher angle of attack, produces more lift at the inboard sections than would be otherwise possible with an untwisted blade. Blade twist results in a more even distribution of lift than we'd see if the blades were untwisted. Because the lower velocity at the root will have a higher angle of attack, and the higher velocity at the tip will have a lower angle of attack. Like tangential velocity, blade pitch angle is relatively easy to calculate. It only requires knowledge of the blade's geometry and the flight control rigging. I used a total twist of 6 degrees from root to tip for my R44 model, and I used the same flight control rigging that I showed in my last video, and set the 75% span section to 2 degrees with the collective full down and 14 degrees with the collective full up. This is with the cyclic neutral. And even though you can see the blade, I still added this graphic vector to represent the blade's pitch angle. This will make it easier to visualize the angle of attack when I add the total velocity vector in a few moments. Induced velocity, which is also called downwash in a hover, is this vertical column of air coming through the rotor disc. We need to find this in order to calculate the section angle of attack. With knowledge of the blade pitch angle and the tangential velocity, we can now apply momentum theory and the blade element model to find the induced velocity. This is also the part where I'm probably going to get some critical comments for not showing all of this work. If you want more details, Gessow and Myers cover momentum theory in Chapter 3 and blade element analysis in Chapter 4. And this is an old book. There are more sophisticated computational methods of doing this today, but I'm not using those. Momentum theory treats airflow through a rotor as a uniform change in the velocity of air coming through the disk. We know this is an imperfect assumption, but we still use it, along with knowledge of the mass properties of air particles, to calculate the thrust produced by the acceleration of air through the rotor disk. This equation is an application of Newton's second law and says that the mass of the air accelerated by the rotor system is equal to the weight of the hovering helicopter. Because thrust is equal to weight, T becomes a known quantity, and we can rearrange this equation to solve for induced velocity. Earlier I said we can use this equation to approximate the lift produced by an airplane wing. Some people call this Bernoulli's equation, but it's not. It kind of came from Bernoulli's body of work on fluid dynamics, and it allows us to compare different size wings operating at different velocities and air densities to experimental wind tunnel data for airfoils. But whatever you call it, it works. It gives a reasonably accurate calculation of the aerodynamic force on a wing section. Here it's adapted not for the entire wing, but for radial elements of a sectioned rotor blade. There are now two equations on the screen, one derived from Newton's second law and the other derived from Bernoulli's principles of fluid dynamics combined with later experimental data on airfoils. Setting these two equations equal and solving the quadratic for VI gives an expression for the induced velocity at any blade section along the rotor span. If we put all of the equations used so far into the spreadsheet, here is the distribution of induced velocity along the span of the blade at 10 discrete blade sections. I use those same equations to drive the induced velocity vector you see on the screen. This vector changes as I raise and lower the collective lever, and intuitively this makes sense. We know that downwash is low when a helicopter is on the ground at flat pitch, and it increases as the pilot pulls up on the collective. The calculated induced velocity is almost the end state of this analysis. We now know for any radial position along the blade, the tangential velocity caused by rotation, the induced velocity through the disc, and if the helicopter is climbing or descending, we can also add the vertical speed to the induced flow. But a comment here, momentum theory only gives meaningful results at low vertical speeds. Guessau and Myers say it's valid up to about 400 feet per minute or 2 meters per second. We now have a horizontal and a vertical velocity vector, the resultant of which is the blade element's total velocity vector. The angle of this vector is downwash over tangential velocity. And since we already know the blade's pitch angle, the angle of attack is now just the angular difference between the blade pitch and total velocity. We now have everything we need to calculate the net aerodynamic force at each blade section. The equation on the screen considers air density, rotor speed, radial position along the blade, the lift curve slope of the NACA 63-015 airfoil, the blade section angle of attack, and the area of the blade element, and the result is the net force at each section. The vertical component of this force is lift, and the horizontal component is induced drag. That answer in newtons is now on the screen, and now here's a chart in US units. The maximum gross weight of the R44 is 2,500 pounds, or about 11,000 newtons. And if you add up each of these blade elements, it adds up to about half of that, but there are two rotor blades, so multiply by 2, and the numbers now add up. And note, I'm not integrating the area under the curve. This is because I already included the blade section length in the equation. The total force is the sum of these numbers rather than the integral. I did one further refinement, and that was to account for blade tip loss by multiplying the force on the last blade section by 0.97. This is the theoretical tip loss for a rotor with two blades and a coefficient of thrust of 0.002, which is what I calculated for the R44. So the goal of this project was to create an accurate simulation of the aerodynamic forces on the rotor blades of an R44 helicopter. Here's a summary of the steps it took to get here. First, we found the tangential velocity of rotation, then blade pitch, accounting for twist and pilot control inputs. We then used momentum theory and a blade element analysis to drive an expression for downwash. From this, we were able to calculate the resultant total velocity vector. The angle between this and blade pitch is the angle of attack. Then we calculated the magnitude and angle of the net aerodynamic force for several blade sections. And finally, accounted for tip loss and summed the forces to find the total lift and induced drag on the rotor blade. Now that we're done, we should ask, is this an accurate prediction of the forces on the blade? And did we have any fun doing this? For the accuracy question, I'd love to compare my results to R44 experimental data, but I don't have any. Guessau and Myers address accuracy in Chapter 6. They say enough experimental data have been obtained to establish definitely the fact that the simple momentum relation does yield reasonably and astonishingly accurate results. So that word astonishingly, I think this is a spherical cow in a vacuum moment in the book. And if you're not familiar with the joke, you should look it up. It's very funny. When I tell it, nobody laughs, but I think it's my delivery. Guessau and Myers go on to say, the good agreement which has been found between theory and experiment may therefore be regarded as a fortunate occurrence wherein very simple concepts give reasonable overall answers to a problem, which in reality involves a very complex flow state. So first it was astonishingly, and now it's fortunate occurrence. And these adjectives are funny in a very dry engineering kind of way. This entire paragraph had to be their attempt at humor. What they're saying is that they use so many of these spherical cows in their analysis that even they are astonished that it works. They even end the paragraph with this: the momentum theory should not, however, be regarded as a completely rational concept. So they're giving us numerical techniques to calculate stuff that we can use to build helicopters based on a theory that they admit isn't completely rational. And I'm okay with this. Too many people look for certainty in places where it can't exist. And it can't exist because we live in a world where natural forces are unseen and poorly understood. Scientists, I think, might view their mission as exposing unseen forces for us, and this is good because it helps us better understand the world around us. Engineers, on the other hand, just kind of awkwardly stumble forward to make progress even in the face of this scientific uncertainty. Engineering is about trying and failing and trying again until you make something that works. And this is cool. Engineers are doers. They make things work, and they do it by embracing those spherical cows with a willingness to step into the arena, even when the critic points out where they might stumble. And speaking of that, if you have any criticism or questions, if I got anything wrong, let me know in the comments. For that last question, was this fun? Heck yeah, it was fun. At least for me it was. I hope you enjoyed watching as much as I enjoyed making it, and I'll see you on the next video.